Okay, well, 2G is all about absolute values, and I mean, here's a basic graph for graphing f of x or y is equal to the absolute value of x. So you can see, for example, that when you put in 2, you get out 2, and let's put a comma on here. And if I put in -2, I also get out 2. Essentially, the modulus brackets, or taking the absolute value of something, changes a negative into a positive or keeps the positive the same. And that's also called finding the magnitude of something. So we're not interested in the direction, we're not interested whether it's positive or negative, we just want to know the rough size of this. So if you have, I don't know, if you're in debt by £12,000, then the size of your debt is £12,000, but in your bank it will say minus 12,000. Debit. Okay, so let's get rid of me as usual. Now, there's a good little book, bit in the book on the properties of absolute values. And there's a good definition of this as well. And you should be aware of what the definition is. It says that the absolute value of A is essentially really two functions. It's saying that, well, you just take A if it's positive, so where A is greater than 0, and you take negative A when A is less than 0. So just think about that one. If we put in, if A was here -5, and -5 brings it back to positive again. Now I'm missing something. I'm missing the case for when we have 0. So I can put that either here or here, because positive or negative 0 is still 0. So let me put it there. Okay, let's just check the definition in the book, see what they do. Yeah, they've done what I've done. They've just put some commas there as well. Okay, now the properties of absolute values are worth considering. And worth just trying to come up with examples to prove to yourself that these are true, or at least to show to yourself, if not to come up with a full proof. So I mean, some of these are pretty obvious, right? I mean, if you put in a number here, the modulus of -5 is equal to the modulus of 5, right? That's the whole point. Some of them are less obvious, perhaps. I mean, it might look confusing, but it's really not. If we say 5 take away 3, sorry, no, 5 take away 5 gives us 0, then 5's got to be equal to 5. You couldn't have 5 take away -5 there, because that would give you plus 10. Modulus of plus 10 is 10. So the only way of getting a 0 out from the modulus is if the difference in between is 0 as well. So if the thing inside is 0. Okay, now this one is really useful in some of the questions which we're going to be dealing with. And it's just saying that if you times the two things together there, that's the same as timesing A, the modulus of A, and timesing the modulus of B. And come up with some different examples. Maybe let's say that maybe A is 2 and B is -3. And let's just check if this is the same. And we see that the modulus of 2 and the modulus of -3, well, we can see there that this is going to give us 6. So modulus of -6, and that's the same as doing modulus of 2 times by the modulus of 3 is essentially, okay, so that's 2 times 3, so that's 6 is equal to 6. Yeah, I mean, so it's working, okay. That's not particularly nice the way I'm showing that. I should really say my left-hand side is equal to this, and my right-hand side is equal to this. Therefore, right-hand side is equal to right-hand side. Therefore, I have shown this to be true in this particular case. It's not a formal proof. Okay, well, you get the idea. That's pretty nice, because it means to say things like this. If you have the modulus of 6, we can split that up into the modulus of 1 and the modulus of 6. Okay, and so we can take out factors if we need to, and we can take out factors in terms of algebraic expressions. So say, for example, I had, I don't know, 5 take away 10x, and that was in a modulus sign. Now we could take out a factor of -1, and there we go, we've got -1. So now we've got 10x minus 5, and now we can split that up into the modulus of -1 and the modulus of 10x minus 5. And the modulus of minus 1 will just disappear, and we're just down to 10x minus 5 because the modulus of minus 1 is 1. So that's pretty nice. That's a useful algebraic one. So number 5 there on the list of properties is worth knowing and worth playing around with. Okay, so this important. Okay, and again, 6 and 7 you can play around with numbers. You know, a plus the modulus of a plus b is less than the modulus of a plus the modulus of b. Now, if you put two positive numbers in there, it's going to be the same. But if you put a positive and a negative in, when you add a positive and a negative together, they're going to kind of cancel each other out. But if we've already made them both positive, then that's going to give us a larger value. And kind of similar ideas here, talking about the difference between two numbers. You can put some numbers in there just to check them out. Those might be useful in a proof, but potentially, but they're not normally used in a lot of lines of algebra, to be honest. This one looks complicated, but it's just like what we were saying earlier on. Remember, if we talked about the common ratio having to be less than 1, that was basically saying that the common ratio needs to be between minus 1 and 1, and that's the same thing as we've got there. And likewise, if we said the common ratio has to be greater than 1, we basically, the modulus of the common ratio has to be greater than 1, then that's leading to us saying, well, that means that r could be greater than 1, but also that r could be less than minus 1. For example, if it's minus 2, then the modulus of minus 2 is greater than 1. Okay, so they're useful. And now we need to know how to graph things, and this is where we're getting back to Desmos. Okay, now in terms of this graph, we really have two functions here. I know this is defined to be one function, and it is a function because every number on the domain has a unique output. So it is a function, but it's defined by really the combination of two functions with domains which are mutually exclusive, which don't overlap essentially. Okay, so really this is the function y equals x, okay, but where x is greater than 0, and this is also the function of y equals to minus x, but when we have x is less than or equal to 0. I'm just going to put less than because it's just easy for me to type there, okay, rather than getting up the list of functions. Okay, so I'm missing out the 0. I wonder if I can just type in an equals there. No, doesn't understand it. Okay. I wonder if I can type equals there. Oh, that was nice. If I type an equals on the end, it changes it to a less than or equals to. I'm learning things as we go. Okay, that's nice. So there we go. If you are typing on Desmos, you can put in a symbol and press equals afterwards, and we'll turn it into an equals. Nice. Okay, so there we go. There's the two functions which are put together to make this single function here. Okay, and it's probably defined in the book as well. Let's have a look at that. Yep, here we go. It's defined to be this sort of two functions here, and it's defined using this this symbol here again, this kind of set symbol. Okay, right. So let's have a little look down at the questions. Now, the questions tell us to come up with our graphs. They tell us to use this form here. Kind of this form here, but then actually sometimes putting a number in front of this as well. So that's what we're going to have a little look at. We're talking about essentially this form here. And this turns out to be a pretty nice form in order to come up with your graphs quite quickly, or your sketches of your graphs quite quickly. But you might have to use those properties of absolute numbers in order to use a little bit of algebra to get down to that point. Now, let's talk about that. Let's sort of unpack that a little bit. Let's get rid of this. Let's get rid of this. And let's talk about the fact that we could have, let's just copy this, okay, because otherwise I've got to use the functions, right? So let's look at, for example, y is equal to x minus 1. Okay, well, that's just pushing the whole thing forward by 1. And again, that's exactly the same as me defining this as f of x and then saying, well, what's f of x minus 1? So you can see transformations are coming in here again. Now, I'm going to tell you at the end another way of doing this, but at the moment I'm just satisfied with using transformations. But at the end of the two examples, I'll talk about a separate way of doing this, so a different version. Okay, now if I wanted to add something on the end, there we go, add on the end there, I've now got essentially this function, okay? So that's pushing the function forward by 1 and then pushing it up by 1. Remember, what happens on the inside is the wrong way around to what you expect, and what happens on the outside it happens the right way around. So it happens in the y direction, and the thing which happens on the inside happens in the x direction. Okay, you should know about transformations already, but if you don't know about them, yeah, do a little research on this one or watch this video again. Okay, right. So now if I wanted to make this twice as steep, I could put a 2 on the front. There we go. So that's now making it twice as steep. So for example, instead of going 1 backwards and 1 up, I'm now going 1 backwards and 2 up. A bit like x squared to 2x squared. So same here, 1 across and 1 up now becomes twice as steep, goes 1 across and 2 up. Okay, so that's me putting like a 2 on the front here. Now you can basically make whatever graph you want now. So if I wanted to put a -2 there, it's going to turn it the other way around. If I wanted to move this thing backwards by 1, I'm going to push it backwards by 1. Let's just check that out again. There was forwards by 1. There was no move at all. So, and then this is backwards by 1. And if we want to move it up or down, then here we go. Let's do a -2. It's going to push this whole thing down. So there we go. If we can put things in this form, then we can sketch these things really quickly. So let's show you that through the questions, and then at the end of the questions, as I say, we're just going to deal with a separate way of doing these questions as well. This is not the only way of dealing with the questions. Okay, so pen back again, and let's look at the question. So we've got example 13 coming up. Okay, so let's determine the domain and range of this and confirm graphically. Okay, so we're not actually needing to sketch it just at the moment, but we're talking about the domain and the range. So in terms of the domain, well, you can put any x value in you want here. It doesn't matter if you have negatives or positives, the absolute sign is going to fix that. So the domain is simply x belongs to your real numbers. Now, in terms of the values which you can get out, your y values, remember that the smallest possible value you can get out for a modulus sign is a bit like squaring something. Because when you square something, you always get a positive answer. And when you take the modulus, you always get a positive answer, or potentially you get 0. So you get 0 when you put in 4. But when we put in 4, this becomes 0. So let's just have a look at that. When x is equal to 4, y is equal to -2, lots of 0 plus 1, we're getting out 1. Now, okay, so 1 is going to be the limit. Now, that's either going to be the maximum value or the minimum value. So let's look at just this number here because we haven't considered that just yet. And the -2 there is telling us that it's going to be upside down, essentially. So a bit like a negative quadratic. And again, when we were dealing with this, when we came up with a -2 here, we saw that the whole graph switched upside down. And if I just go to the original f of x, this red one here, if I put a minus in front of it, it's going to turn it upside down. Okay, if you want to just think about that one for a moment, if we're saying, if we're putting in 2, for example, then when you put in 2, the modulus of 2 is 2, and then the negative of that is -2. So we're just taking all of the normal heights that we get from the modulus graph and then just negating them. We're going to reflect it over the x-axis. Okay, so in this case, we're going to have y also belongs to the real numbers. A bit closer. The highest value you can possibly get is 1. So x is going to be less than or equal to 1. The graph is upside down. Now, in terms of this graph, you can quickly see that we're getting out when x is equal to 4. Okay, you're getting out that height. So when you're putting in 4 there, you can see you're getting out the height of 1. And you know this graph needs to be upside down. So essentially, the normal graph of the modulus of x has been shifted forward by 4 and up by 1. So the apex, if you like, or the turning point is moved to there. So that's just 2 translations or a vector translation of 4 across and 1 up. Okay, that's what's happened. That's to describe the transformation. And then we know this is going upside down. So it's going to be something like this. It's going to be upside down. And we also know that it's been scaled by a factor of 2 in the y direction. So that means to say that when we go 1 across here, we need to go 2 down. So my graph is not particularly good there. So I know that when we have 1 here, we're going to get -1 when we plot 3. So my axis scales are not the same size, are they? But okay, so we're going to get this thing here. That's not very neat, but you know, you can put that coordinate point on, and you can put the coordinate point on for 5 and -1 as well. Okay, so the way I got that was by going 1 across and 2 down. So that was 1 across here and 2 down. Okay, confirm it graphically. Well, you can type it into your calculator, of course. You can type it into Desmos. It's always good to get faster at using your calculator, so you can type it in there. Again, at the end, I will tell you another way of doing this one, but for the time being, I'm satisfied with that. Let's look at the answer. So let's just take this one here. And yeah, and you can see here that just like I was saying, here's our apex or our turning point. And if we go 1 back and 2 down, we get to the next place, and 1 forward and 2 down, we get to the next position as well. Good, right. Okay, example 14, and then we get to exercise. Okay, so for example 14, let's determine the domain and range of this function here. Now, this is where your algebra comes in, using the absolute value. So we can split this up into -1. Remember, we did this earlier on, and times by what do we got here? 2. Actually, we can take out -2 here as a factor, and that's going to leave you with x and what do we got? -1 there. That's just factorizing the thing on the inside, and then we've got this +1 on the end. Now we can then split that up further, and we can say, well, that's the modulus of -2, the modulus of x -1. Oh, that's good. That's the form that we want. And then -2 is the same as 2 if we take the modulus of it, or the absolute value of it, and then we put the +1 on the end there. Okay, so in order to sketch this function, we can see that it's been moved forwards by 1 and up by 1. That's from these 2 translations here. And it's also twice as steep as the regular modulus of x graph. So if we go 1 backwards and 2 down, we'll get to -1, so it should go through there, should go through there. Let's just make it clear where these things are. And at 2 should go through there as well. So there's our graph. If we join that whole thing up, that should be our graph in this case. Now, of course, you can put on your x, you can put on your y, and you might want to just show that this continues further here and here, but that will be sufficient for your sketch. And of course, you can check that one out online. Okay, let's have a little look at this. Oh, I messed up. Can you see how I messed up? Yeah, I messed up on this one. I'm getting confused with the previous one. I'm sorry. Like, big sorry for this one, okay? And hopefully you can see how I've messed up on this one. Okay, you can see that in fact there's a 2 in front. So it means it's this way round. Sorry about that. I was getting confused with the previous one. So I just need to take that one back for a moment. Put this back. Okay, so where we had this turning point here, we need to go to 3 here and 1 here, and there's 1 and there's 0. 1, 2, 0, 1, and there's your point there as well. It's going to go like this. Sorry about that one. Okay. Hopefully you've carried on and listened to this point. Okay, no, that's good. Okay, sorry. Okay, so I said I was going to deal with an alternative version of this, an alternative way of dealing with these questions. So let me go back to example 13. Okay, so example 13 is this one here. Now, you could deal with this one by sort of building up, by starting off with this here. So you could just think, here we go. We're talking about, to start off with, what's the modulus of x minus 4 graph? Well, first of all, what's the graph of x minus 4? Well, x minus 4 goes through 4, minus 4 here, and 4, because this is the graph of y equals x minus 4. So goes through the y-axis, intercept of minus 4, and it also goes through the x-axis, intercept of 4. Easy to get out, and it has a gradient of 1, pretty straightforward. Now, of course, this part is not valid for modulus functions, so this part needs to be reflected up here. So at that point, you can then reflect this up here, and now this is essentially y equals minus x plus 4, so the negative of this one here. Okay, but now the entire graph, when we put it together, is now the modulus. So let's get rid of that. So it's going through 4. Now if, okay, so we've got 4 there. So now if we're looking for the actual graph itself, now we need to multiply by minus 2. Well, multiplying by minus 2 is going to reflect over here. So, for example, the 4 is going to become a minus 8. Okay, the 0 is going to stay at 0, something like this. 0 is there, and then when you're getting 8 over here, that's going to reflect down. That 4 is going to reflect down to minus 8 as well. So we can join that thing up, and then you can deal with the plus 1 at the end as well. And so you can add your 1 on here as well, and everything is going to shift up by 1. Now this is obviously a longer process, but this is the process you can go down if you're not confident with using your algebra with modulus signs, modulus brackets. Okay, so if you don't see, for example, in the next question, okay, so for question 14, if you don't see that you can factorize out the minus 2 and then split up the modulus and then change the minus 2 to a plus 2, if you don't see that, you can still do this whole thing. Take this one as well to show you this also works. Okay, so here we go. And so for this one here, you can do you can actually plot the graph of 2 minus 2x to start off with. The 2 minus 2x is going to cross the y-axis at 2, but it has a steepness of minus 2. So it's going to go through 1 here. But so that's going to go like this. Let's go through those 2 there. Of course, the modulus is then going to bounce upwards on the other side. So that's the modulus of 2 minus 2x, and then we can just add 1 onto that. So we could do that as our first graph, and then we can just add 1 on. And that actually turns out to be quicker there. So add 1 on is going to go through 1, 1, and then it's going to go through 0, 3, and it's going to go through 2, 3 as well. Okay, I'm not sure actually if I answered the domain and the range in this question. So let's just go back to this, and it's just, once we've got the graph, it's actually really easy to come up with our domain and range, because we can see that this graph is above, so y is above 1, so y belongs to the real numbers, but it has the condition that we are greater than or equal to 1, and x, of course, is any real number. I think I forgot to say that. Okay, well, thanks for listening in. Next time round, after you've done those 10 questions there, next time round, we're dealing with just solving using absolute brackets, modulus signs. So just solving, which could be done algebraically or could be done using the graphs. But anyway, that's next time around. Okay, thanks for listening and see you next time.